Okay. I hope you can see me. The presentation is visible. Uh, so let's wait for a couple of more minutes if anyone else wants to join, and then we will start discussing the assignment number 5. Okay. Okay, let's start then. So, just for the formal introduction, myself, Prerak, and I'm taking this fifth weekly live session. I will be discussing assignment number 5. Um, the course name is an invitation to topology, and the previous recordings are available on my YouTube channel, which is Maths with Prerak Deep. You can search this Maths with Prerak Deep on YouTube search bar, and you will find out my channel. Okay, all the recordings are available over there. This week's recording will also be uploaded once it's done. Okay. Um, Question number 1. So this assignment is all about the connectedness. Okay, so we will be discussing questions on connectedness and try to understand the concept better. Okay. In between, if you find any argument given by me difficult to understand, you can stop me, ask question. You can write in the chat box, and then we will have a conversation. Okay. Which of the following spaces are connected? Okay. Option A, R with the standard topology. Option B, Q with the subspace topology from R. Option C is N with subspace topology from R. Option D is R with discrete topology. Okay. So I will give you a minute to think about this, but before, let me recall what do we mean by connectedness. Okay. So quick recall to that. We say a subset A in X is connected if there is no pair of open sets U and V such that okay. So I have written down this definition for the subspace A, assuming that A has a subspace topology with respect to that. But you can just, we say a topological space. So we can, let me modify this definition to a simpler setting. We say a topological space X tau is connected if there is no pair of open sets U and V such that the union is equal to X and their intersection is empty. Okay. And further, such such a pair of open sets U and V is called a separation of X tau. Okay. So in other words, if there exists a separation of a topological space, then that space is not connected. Okay. So this is the recall, and we all know what do we mean by standard topology, subspace topology, and the discrete topology. So I will give you a minute to think about this. And I see Rudra joined just recently. So today's topic of discussion is connected spaces, connectedness of a topological space. We will be discussing a few problems from that. Okay. And uh, as we do, I will write a question. I will give you a few minutes to think about that question, and then I will discuss the solution. Okay. So this is the first question that I'm discussing. Okay. And now I give you a break, like 2 minutes to think about this, 2 or 3 minutes, and how whatever time you need to think, and then we will discuss the solution. Okay. Okay, that's a very good guess. If you guessed it, if you have solved, then it's also good. So option A is the correct answer. Um, let Rudra answer, and then we will discuss the solution. And okay, uh, yeah, that's correct. So let me discuss the solutions. Okay, so let me discuss B, C, D first, and then we will go back to A. So okay, why B, C, D are not the connected spaces. So whenever you need to prove that something is not connected, uh, then you need to give a separation. Okay, and if you want to prove that something is connected, then you have to start with the assumption that there is a separation, and then you give a contradiction to that assumption. Okay, so there are only two ways is to do that. So for BCD, because you want to prove that they are disconnected, we need to produce separation. Okay, so let me start with B, Q with subspace topology from R. Okay, so in this case, we can start with any irrational number. Okay, so we can start with any irrational number. Let's say a square root of 2. So square root 2 is a irrational number, right? And if I consider this open set, okay, and take my V to be this open set, then these are two open sets in R with the standard topology, right? And if I want to consider in the subspace topology on Q, I just take their intersection. So let define U prime to be O U intersection Q and V prime to be V intersection Q. Okay. And now clearly U prime and V prime are open sets in the subspace topology on Q. Okay. Um, right. And further, what do we know? That U prime union with V prime is equal to Q. Okay. They contains all the rationals number, right? And further, we also know that their intersection is also empty. Okay. So yeah. Now because of these two conditions, U prime, V prime is a separation, is a separation uh, of Q. Okay. And because of this, thus Q is not connected, right? Okay, so we have new joining. So I'm discussing questions from the connected space of topology, and this is the first question that I'm discussing, right? The recordings of my these sessions will be available on my YouTube channel, Maths with Prerak. You can go and have a look at over there. Okay. So I think this must be clear why Q is not connected subspace of R. Now let us look at um, the similar approach we'll go through in the case of natural numbers. So natural number is not a connected subspace of R. Okay. Again, we need to start with something which is not natural number. So you can take, you can, let's say, take half. So it is in R minus natural number. Okay, it is not a natural number. And you can consider U, which is half to infinity and a minus infinity to half as V. And again, you define U prime to be the intersection and V prime to be the intersection of V with N. And clearly U union with V prime is equal to the natural number, and U intersection with V prime is equal to is empty set. Thus U prime V prime is a separation of the natural number, and hence N is not a connected subspace. Okay, so this is also the similar approach. You can also say that N has a discrete so the subspace topology on N is discrete. Okay, it is a discrete topology on N, and anything with discrete topology is not connected. That is what option D is. So R with discrete topology. Okay, so R with discrete topology, that means every singleton set is a open set. Okay, any subset of R is a open set, right? So you can get partitions. That is very easy. So you take any subset. So consider, uh, so take a non-empty subset U. Okay, take a non-empty subset A of R, right? Now clearly A is open, okay, because it's a subset of R, and R is with the discrete topology. And further you take your A complement A, so you can say A and A complement are open sets in R, right? R with discrete topology. Okay, and further, moreover, A union with A complement is equal to R, and A intersection with A complement is empty, right? So thus A comma A complement is a separation of R, right? It's a separation of R. Thus, um, hence R with discrete topology is not connected, right? So this is also trivial, and you can use this idea that any set with discrete topology is not connected. So you can generalize this argument to any set. Okay, it need not to be R in this case. R has no importance in this proof. So you can take any subset and you can give discrete topology to that. Any subset with discrete topology is not connected. So now n with subspace topology from R is actually discrete topology on n. Okay, and that will also imply that n is not connected subspace of R. Okay, with that being said, now we come to A. So A is A with standard topology. So R with standard topology. So again, we start with that there is a separation, and if there is a separation of two open sets, then their intersection has to be empty and their union has to be equal to R. But if that is the case, uh, right, right. So there we use this theorem 4.1, which says that a linear continuum is connected in its order topology. Okay, and it is an exercise for you to check that R with the usual order is the linear continuum. Okay, so you can apply this theorem, which is this theorem is part of the lectures. Uh, so you can apply this theorem and you can get that it is a ordered with respect to the order topology. It is uh, an connected space. Okay. So are these things clear to all of you?
Yes, sir.
Good. Now we can move ahead with another question. Now, which of the following spaces are connected? Option A, as a subspace of R2 with a standard product topology times Q, interval times Q as a subspace topology of R2. Okay. Similarly, Q times Q as a subspace topology of R2 with the standard product topology. And option D, the unit ball BD of centered at x0 of radius 1 in R2, right? So this is clear. This is centered at x0 and with radius of 1. Okay, so this must be clear. And D is the Euclidean metric, which is the usual metric. Okay, so again, so here is one thing to notice is that the product topology, product of connected spaces is connected. That is one thing you need to notice, you need to keep in mind. And other thing is also is that the projections, continuous images of the continuous Images of connected spaces are connected. With this and that in mind, you can think of trying to find out which of the four options cannot be connected or connected. Okay. Again, I will give you a few minutes to think about this problem, and then we will discuss the solutions. Yes, that is a correct answer. Let other also answer, and then they are all. If you guys, all of you, are thinking the same way, then we can move ahead with the solution. That's the correct answer. Okay. Okay. Sure. Then now I think we can discuss the solution then, if all of you are comfortable. So, so let's first discuss why B and C are not connected. So, for that, you need to construct a separation for both of the spaces. Now, we already know that intervals are connected spaces, right? Intervals are connected subspace of R. Uh, but for Q, and for Q, we have seen Q is not a connected subspace of R. This is what we have seen, right? Is not a connected subspace of R. So now we want to use the similar separation in the product topology. Okay. So what separation did we have? We had this separation, this union with minus infinity to root 2. This was the separation U union V, right? And now I just multiply this with the interval, right? So now this itself will be an open set in the subspace topology. So this will be an open set. So this is an open set inside this product topology under the subspace topology from R2, right? And similarly, the other set would be, so this will be my U prime, this will be my V prime, root 2 to infinity, which will again be an open set in the product topology of interval times Q, which is coming from the subspace topology of R2. Okay, right. And now we can clearly see that U prime intersection V prime is empty. Why? Because the second component in the product uh, have trivial intersection. Okay, that's why have empty intersection. That's why their product will also have the empty intersections. Okay, that must be clear. That can be treated as exercise also. That is a small check for you guys to think. And thus this, and also their union is the whole product interval times Q. Okay, so thus U prime V prime is a separation of the product in R2, and hence it is not connected. Okay, so we use the fact that Q is not connected and we did this. Now similarly we can construct, now similarly for option C as well, we can construct a separation, and you can also guess the separation, what, how will it look like. The separation will look like minus infinity to root 2 times minus infinity to root 2, mm, okay, you can just treat Q times minus infinity to root 2, uh, so you can take this separation and you can check that their union is equal to Q times Q and their intersections is trivial. Okay, is this clear? This has to be, if this is clear, we can discuss the other things. Okay, now option A says interval times interval is a subspace of R2. So there I mentioned one theorem which is part of your lectures. Let me write that down. So it is from theorem 3.4 of lecture 2, that says let X alpha be a collection of, be an arbitrary collection of connected topological space, then X, which is defined to be the product of all these topological spaces, is also connected in the product topology. Yeah, that is important. It is not under the box topology, okay? Because this arbitrary product can have two topology that we have seen last time, one product topology and the box topology. So this will be connected in the product topology, and we will see later an example. This will not be connected in the product topology. Okay. Um, yeah. So by this, what do you have? You have two arbitrary sets. So this is an open. This is a connected set. This is a connected subspace of R. Similarly, this is a connected subspace of R. Yeah, this is also a connected subspace of R. So both are connected subspaces of R, right? And thus their product. So their product will look like, this is their product. So this product, their product will also be connected in the product topology. So because this is a finite product, so in finite product, box topology and product topology uh, coincides. Okay, in the finite product of spaces, box and product topology are same, so it doesn't matter. So we only have the product topology, so it is also written in the question, that is product topology space. So this will be connected. Okay, so this is directed from the theorem. Now option D. So option D is, you have given this ball centered at x0 with radius 1 in R2 with the subspace topology induced from R2. Okay, so let me draw the figure. Okay, so this is your circle. Let me draw a bigger one. Yeah, this looks fine. Yeah. Okay, so this is your circle. and this is your point x naught, and this is of radius 1. Right now, what how do we prove that this is a connected space? So we, as I said earlier, if you want to prove something is connected, you start with the separation. Okay, so suppose BD x naught. Yeah, it is convex. For convexity, I don't think so you need any topology on it. It is convex in nature. But the point is like, so convexity will prove the, okay. So the argument Thangeshwaran is giving is also correct. Okay. But it is not being covered in your syllabus. That's why I'm skipping that. And that's a simpler argument which Thangeshwaran is giving. So let me discuss what he's saying. Okay. So let me mention it as alternate approach, the the simpler alternate approach. So as he clearly mentioned that it is a convex space. So BD x naught 1 is a convex space, right? And what do we mean by convex space? It means that given any 2 points, you can find out a line sitting inside that space, a straight line. Okay, that's what important for the convexity. You can find out given any 2 points, you can join them by a straight line, and that straight line also contained inside the space. And this convexity is irrespective of the topology. You don't need any topological structure to define convexity. You need to have uh, some. You need to have linear structure, which is like vector space structure on it. Okay, so you need to have some linear structure or affine structure on it to define the convexity. You don't need the topological structure to define. Okay. With that being said, so given any 2 points, you can join them by a line, and that line should also contain inside your space. That is what convexity means. So let's say this ball of radius 1 centered at x naught is a convex space. And now this convexity is nothing but, in topology, you can, this convexity gives you a path, in particular joining any two arbitrary points. Thus, uh, given A and B in your ball, given 2 points A, B in your ball, uh, there exists a line, a straight line, straight line, straight line segment in particular, joining them, which can precisely be given by this uh, equation, that is t times a plus 1 minus t times b. Okay, that's a parametric equation of this line, right? Mm, okay, so now this basically gives you a path joining a to b. Okay, this gives you a path joining a to b, and thus hence bd x naught 1 is a path connected space. Now this path connectivity, this is topological term. Okay, convexity is not a topological term. So path connected space, and then you need to use this theorem, which you will see in the upcoming lectures, I suppose, that path connected space uh, is a connected space. Okay, path connected space is a connected space. So with this theorem, you prove that ball BD of x naught 1 is a connected space. Okay, so this is the alternate approach and the shorter approach. Okay, but it requires you to know what do we mean by path connectedness. Okay, and I suppose you guys have not seen path connectedness as of now. If you have seen, then I can stop here with the proof. If you haven't, if you don't know what path connectedness, I will give you alternate proof also. So it is up to you. So my question to you is, do you guys know what do we mean by path connectedness of a space? Okay, Tangeshwaran is asking, yeah, it's in the next week content. I know that. So that's why this is a simpler proof to this thing that the ball is a connected space. I know that it's a next week content. Okay, so let's come back to the proof that I was thinking to give. For that also I need this diagram. Okay, so right. Okay, so right. So now, so again, I said as before that if you want to prove something is connected, you start with a contradiction. You start with a contradiction that you start with the assumption that it is not connected, and then you prove that it's a contradiction. Okay. So suppose your ball of radius 1 centered at x naught is disconnected, which means that it is not connected, or in other words, it has a separation. Has a separation. That means A and B. All right. A and B, two sides. Right. And now, what I'm going to do is I'm going to consider these projection maps. So pi 1 is a map from x times y to x. So in our case, the projection map will be from r cross r to r. Okay, so first projection will be on the x-axis, and the second projection will be on the y-axis, and I will call them x pi x and pi y. Okay, now these projections map, you can check that they are open maps. Okay, why? Because why they are open? Because what is the open map? Open map is taking an open set, its image must be open. And what topology do we have on r cross r? R cross r has a product topology coming from r only. Okay, and any open set in r cross r looks like product of two open sets. Okay, so if you are taking, if you are starting an open set which is a product of two open sets, and you project it to an open set only. Okay, you, because you are projecting to the first coordinate, in this case pi x, you will project to the first coordinate, which will give you the open set. In the second case, you will project to the second coordinate, which is also an open set, so you will get open set in both cases, right? So these maps are open. This is a very simple check for you to do. I have given you the idea also. So these are open maps. So they take image of open set to an open set, right? And now, so does um, pi x of A, pi x of B, pi x of pi y of A and pi y of B, these are all open sets in R, right? now suppose suppose that pi x of A intersection with pi x of B is non-empty. Okay, their intersection is non-empty. Okay, so yeah, so now in this case, um, okay, so under this projection on pi x, right? So if you restrict your map pi x to your ball, so where will it send? It will map your whole disk to this interval on pi x. Okay, -1 to 1, x naught -1 to, so this point will be x naught -1 comma 0, and this point will be x naught plus 1 comma 0. Okay, this will be the image of pi x. So image of pi x will be x naught -1 to x naught plus 1, right? Similarly, image of pi y of bd 0 x naught 1, this image will also be same. Okay, but it will be on the y axis. Okay, so it will be on the y axis. Is this clear? Is this clear to all of you what I'm saying? Okay.
Yes, sir.
Okay, good. So now, what do we want? We want to prove, we assume that pi x of A intersection pi x of B is non-empty. Okay. If you assume that, that means what? That means there is a point M in pi x of A intersection with pi x of B, right? There's a point in the intersection. And if you take the pre-image of M, what will you get? So let's say you have a point over here. So this is your point M. Okay, it's in the intersection of pi x of A and pi x of B. And if you take the pre-image of that, what will you get? You will get this whole line. You will get, right? You will get this whole line. Okay, and you can also know this interval. What is this interval? So this interval is, you can also tell the interval, right? So this pi of M is nothing but M times some interval. Okay, interval in the y-axis, the direction of y-axis, right? And now what is that interval? That interval you can also tell by knowing this length. And what is this length? How do we calculate this length? This length is nothing but, you just apply the Pythagoras theorem. So this length is M. So basically this length is uh, M minus x naught. This length you want to know, and the length of the hypotenuse is 1. Okay, so what will be the length of the other thing? So let's call that to be the length y, let's say. So y is nothing but plus minus of, so it has to be positive, so it is plus only, plus a square root of 1 minus m minus x square, right? So this will be the length. So what will be that interval? That interval will be now x naught minus or yeah, yeah. So this interval will be what? This interval will be, yeah, x naught minus y and x naught plus y. Exactly. And what is y? Y we know. Y is nothing but this value, which is, so this value is not important. The point is that the preimage of M under pi map, it will be M times an interval. That is what important. And you can also see in picture also, then what will be what that preimage will be. And you can also write it in mathematics also. This is an interval. Okay. And clearly you can see that this interval, so pi x m, which is m times an interval, also intersects with b, right? uh, Not b. What do I want to say over here is that, mm, right. So now, yeah, now because pi x m is equal to m times im, which is nothing but an interval. Okay, so it is connected, is connected. That is what I want to say. And now since it is a connected uh, subset, so it has to be in either of the separation open set. Thus pi of x of m either has to be in A or in B. Okay, it can't be in both. It has to be either in A or either in B. But if it's in A, so if it's in either of that, then m is only contained inside pi inverse of A, and m is not part of pi inverse of B. That is pi inverse. That means m is not contained inside the intersection of A and B, right? So which is a contradiction, because we started with that m is in the intersection of these two things. So it is a contradiction. Thus intersection of A and intersection of pi in pi x inverse of A intersection pi x inverse of B has to be empty. Okay. Okay, so this has to be empty. So now, so this argument, whichever is on the screen now, is this argument clear to all of you or not? Because this is the last technical part, I would say. And then we okay. So I assume that the silence is yes or maybe confusion. Uh, but I'm assume that this argument is clear. Okay, this basically says that uh, yeah, that these two things are mm, yeah. Here I'm a bit wrong. Pi x of a, pi x of b. Yeah, their intersection is empty. Right. Now this is clear. Now this is fine. Right. This was a mistake. Inverse shouldn't be there. Right. So their intersection is empty. Right. And thus, what do we have proven? We have proven that now pi x of a and pi x of b are open sets in R, right? So, and moreover, pi of x a, pi of x b is equal to minus 1 comma 1, and their intersection is empty, and their intersection is also empty. So this implies that minus 1 comma 1 has a separation. Thus minus 1 comma 1 is not connected, which is a contradiction. Okay, so our initial assumption must be wrong, and the initial assumption was bdx not 1 has a separation, so this must be incorrect. That means ball of radius 1 centered at x naught does not have a separation to it, so this is a contradiction to from this. Okay. Okay, so I will give you a minute to think about this solution, and then we will move ahead. Okay, if there is no question, then we can move ahead. All right. Which of the following subsets or subspaces of R2 are connected? Option A, X is given by the union of LQ, where LQ is in Q is a rational number, and LQ denotes um, LQ is a straight line passing through the origin with slope Q. Okay. B X is a union of two sets where A is product is uh, product of two intervals, open intervals, and B is all xy in R2 such that x is in 0, 1 and y is in Q intersection with 0 and 1. Option C, x is the graph of the function. Okay, in R2. X is a graph of the function where f is a continuous map. Option D is x is a equation. X is a circle in R2 centered at origin of radius 1. Okay. Again, I will give you a few minutes to think about this question and then we will discuss the solution. Okay, so you said that C and D are connected. Okay, let's wait for others also to guess. Okay. Yes, all of these answers are correct. That's a correct guess. Okay, let me discuss you the solution now. So I will give you an intuitive proof of all of them. I will not discuss proof in detail. Uh, yeah. So for example, for the first, you can draw that it's a line that is passing through all these points. So here I want to write down one theorem which says that um, continuous image of a connected set is connected. Okay, continuous image of a connected continuous image of a connected set is connected. Okay, so let me rewrite it. Let let f be a map from x to y, be a continuous map, and A be a connected connected subspace, then f of A is also connected. So this is the result that uh, we want to use in this proof. Okay. So for example, um yeah, for example, D, how do we use it that in D? So D is what? D is nothing but an image. You can define a map F from an interval 0, comma 1 to, or more precisely 0 to 2 pi to R2. Okay. And this map can be defined to be cos t, comma sine t, right? And now clearly you can see that this map is a continuous map. Okay. It is continuous in both of the coordinates. So it is a continuous map. And what is the image of this map? The image of this map is precisely the circle, uh, precisely the circle or the space X given in the option D, right? So it is an image of a connected set. And we know that interval 0 to 2 pi is a connected subspace of R. So it is a connected, it's an image of a connected set, hence it's connected. Option C. Option C says the graph of a continuous function. Okay, so you can define a new function g, right? You can define a new function g from x to R2, right? You can define a new function g from x to R2. I suppose it's from, yeah, you can define a new function from R to R2, right? And this function can be defined in this way that x going to x comma f of x. And now uh, the first coordinate is nothing but the identity map. Okay. And the second coordinate is given to be a continuous map. It is in the hypothesis. So this, so G is also a continuous map, right? So G is also a continuous map. And further we know that R is a connected R is a connected space with the standard topology on it. So the image of R under G is also connected. All right. So yeah, so that's and what is G of R? G of R is nothing but space X given in option C. Okay. So yeah. So this is also this. So are these two options? Are these two answers clear to all of you?
Yes, sir.
Okay. Good. And now let's see B. What is B? So B is union of LQs where Q is rational. Okay. If you draw this thing, So like this you can draw, like this you can draw more uh, lines. Okay, so these are all lines passing through, um, yeah, these are all lines passing through the origins. Okay, this is your origin point, 0 comma 0. Okay, this line is of slope 0, this line is of slope infinity, this line is of slope 1, this line is of slope -1. uh, yeah, so there are only 4 lines that I've drawn. Okay, um, and you can draw many more lines. So now you need to say that this set is, um, yeah, so this set is uh, connected. So what we are going to use over here, and this set is connected in the subspace topology of R2. So you want to prove that this is connected in the subspace topology of R2. Now, what is the subspace topology of R2? Subspace topology on R2 is equivalent to the product topology on this space. Topology on this space. Okay. So with this is a mention. So we just need to prove that LQ, each for each Q in R, for each Q in Q, LQ is connected. And how do we prove that LQ is connected? And for that, one can define a map from R2 to be in this way. You take um, yeah, T uh, goes to T comma QT. Okay, so this is the map. And now clearly you can see that the first coordinate is the identity. The second coordinate is nothing but a linear map. So both of them are continuous map in the standard topology of R2, in the standard topology of R. And hence in the product topology also, this will be a continuous map. Both of the coordinates are continuous. So it is a continuous map, right? And now R is a connected space. So f of R, which is nothing but LQ, is connected. All right. And now we use this theorem that I have mentioned earlier as well, that union of, yeah, arbitrary union of connected subspaces. Given arbitrary union of connected subspaces, their union is also connected in the product topology. Okay, so here we have the countable union of the connected subspaces under the product topology. So it is, so X by that theorem is connected by theorem above. Okay, so this was option A, I think. Yeah, this was option A. So option A is also clear. Any question in this?
Yes, sir.
Yeah.
Sir, what if we, sir, but if we consider, let us take a line with slope root 2, then wouldn't
No,
that
it's a
be a,
rational. Slope is rational.
okay, sir.
Yeah, slopes are rational. That's the point we have. Any other question? Okay. Now let's discuss the last option. Uh, option B. So option B is A is a product of two open sets. Option and B is a set given in this way. So let me write down both of them. So X is product of sorry, A is product of these two things, B is set of the subset of R2, um, such that x is in 0 comma 1 and y is intersection of q with interval, right? Now what is B actually? Okay, so what is A is, you can, let me draw that again, let me draw this. So this is your space A, all right? This is the open space because the product of two open sets, so it is open in R2, and um, yeah, so this is X, this is Y, and this is your A, right? But the boundaries are not included. Okay, the boundaries are not part of this is a square. So this is a square, but the boundaries of this square is not included in A. Okay. Um, yeah, and now what about B? So B is, uh, x is equal to 0 and x is equal to, so x at 0 and x at 1, 1 comma 0 and 0 comma 0, okay, times q times the interval. Okay, right. So we only want to, right, so we only want to look at the, take y is equal to 0 and x is equal to, so y is equal to 0 is going to be the x axis times this set times x equal to 0. Okay, so this will give you, sorry, this is the origin only. uh, all right, so y is equal to 0 and y is equal to, yeah, so 1 times y is equal to 0 and 0 times y is equal to 0, right? Y is equal to 1 times,
Sir, but Q intersection the interval will be the interval itself, so I will belong to the interval only, no?
no, q intersection with, intersection of q with the interval will not be interval. It will be a subset of, uh, there will be irrational numbers, okay, in the interval, so it can't be the whole interval, right?
Yes, sir.
Yeah. So what my point is that rest of the points except the boundaries 0 and 1, so except, so what I'm trying to say over here is that you need to notice that except y is equal to 0 and 1, whatever is in the interval, whatever is in the, q intersection open 1 comma 0, this will already be part of the A. This is already be part of A. Okay, times, 0 comma 1, this will already be part of A. So we only, so the only point that is not part of A is y is equal to 0 and y is equal to 1. All right, so when you take y is equal to 0, and what are the choices you have? So y is equal to 0, will be, you are on x-axis, right? But on x-axis, what points are you taking? 0 and 1. So it will be singleton 0, singleton 0, singleton 1 times. So basically, you will have only these many points: 0, comma 1, 0, comma 0, 1, comma 0, and 1, comma 1. Okay. So basically, these boundary points will also be included in this A. Okay. And now you need to say that this is a connected space or not. And let me give you a hint for that. You need to use this theorem from. So I will leave this as an exercise for you guys. This is obviously looks that it is connected, and it will be clear when you, in the next lecture, when you will study about the path connectedness, then it will be easier to prove. I don't want to give you another proof for this, but if you want to pursue the proof, you can just follow this theorem from lecture 2, 3.3 from lecture 2, that says that let AB be subspaces of X, and A is a subset of B, B is a subset of A closure, then B is connected if A is connected. Okay, so in our case, X is what? X is A union B. Sorry. So here AB is different. Okay, so let me say X here is, okay, let me say A prime B prime. That will be easier. Yeah, so these A things are different. So here space X is A union B, right? And space A is your 0 comma 1 times 0 comma 1. Okay, that is A prime is 0 comma 1 times 0 comma 1. And if you take the closure of this, you will get this. So this is already given to be connected. This, you know that this is connected. It's a product of two connected spaces. So by the product topology, it is connected. Okay, and their closure is this going to be. And now what is B prime? B prime is A union B. Okay, that is your B prime. That is X. And this is actually, and this X is actually subset of. So we know that A prime. So we know this thing, that this is contained inside your A union B, right? And this is contained inside your A prime closure. That means this part. All right. So yeah. So by this theorem, this is connected, and so this will be connected by theorem 3.3. So this is the proof by this theorem 3.3, and you can also prove it by using path connectedness of these spaces, which we haven't discussed now, but that will be easier if we could have. So yeah, okay. So any other question on this?
No, sir.
Oh, good. So if there is no more question, then we can stop here. Okay. So I hope to see you next week as well. Thank you for joining. The recording will be available on my YouTube channel. If you want, you can go and check it out later. Okay. Bye, everyone.
Thank you, sir. Bye, sir.